Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 68, the last problem of this chapter. And this problem tells us that benzene itself, so let's draw a benzene. The carbons on the benzene itself, and its carbon 13 NMR, absorb at 128 ppm. However, the carbons of a substituted benzene like X and Y will either absorb upfield or downfield from this 128 ppm value, depending on the identity of its substituent. Explain the observed values for the carbon ortho to the given substituents in the monosubstituted benzene X and Y. So this actually brings up an interesting topic, hopefully to come up in the next chapters to come, as electron donating and electron withdrawing substituents on benzene. So what do we know about being upfield or downfield shifted in an NMR? So if we're upfield shifted on an NMR, we're on the right side of the spectrum, and that means we have high electron density on our nucleus. So on our carbon nucleus, we have a high amount of electron density, shielding this nucleus from the applied magnetic field from the NMR magnet. So in effect, we feel a lower effective magnetic force on this carbon nucleus. Therefore, in order to cause that spin flip or resonance in the carbon nucleus, we need to apply greater amount of energy or greater frequency to this nucleus to overcome the countering or the anti-countering effect from the electron density shielding the nucleus. We need to add more energy to counter this opposing effect from the electron density to allow that spin flip to occur. So because we need to add more energy, we will be going right on our NMR spectra towards the 0 ppm value. And I know that's kind of confusing because we go 0 ppm to 14 ppm from right to left, but in terms of field strength, we go from left to right in increasing magnetic field strength. So that means that because we need to have higher frequency, we need to be on the right side of the spectra to gain more energy or more higher frequency to cause a spin flip to occur when we have higher electron density on a carbon nucleus. But now, opposite, if we're downfield shifted, that means that we have electron density being taken away from our carbon nucleus. So now there's less of that opposition around this nucleus for the magnetic field force of the NMR to counteract. So therefore, because there's less of an opposition, we are going to be on the left side of our NMR spectra. And the reason for that is because of that lower amount of opposition. So therefore, we are going to require a lower amount of frequency or less amount of frequency than something that is shielded to cause that spin flip to occur. So because we're on that lower amount of frequency, if we extract that up to our NMR charts, we're now going to be on the right side, or sorry, on the left side, downfield shifted on our NMR spectrum. So now we have low electron density around our nucleus, making it lower amounts of opposition for the magnetic field force to be felt from the nucleus, therefore requiring lower amounts of frequency to cause that resonance or spin flip to occur, therefore being on the left side of our chart on our NMR spectra. So now, this is where electron donating and electron withdrawing substituents come in. So now, if we see we have a nitrogen here on compound X, so nitrogen has a lone pair electron. So this nitrogen can actually donate electron density to our benzene ring in a form of resonance structure. So if we make a double bond here, we can move this pi bond to this carbon nucleus here. So we can actually form now a resonance structure as a positively charged nitrogen, but now we have a lone pair electron on this carbon forming a carbocation. So now the negative charge and increased electron density makes this carbon more shielded, therefore it's going to be absorbing upfield. And when we absorb upfield, we're getting closer to that 0 ppm value. So now it's going to be less than that 128 ppm. So that is why it's at 113 ppm. But now what about this group? Well, this group, if I were to redraw it in Y, we see that we have an aldehyde here. So I can also draw a resonance structure for this molecule using this pi bond. So now make a bond here, making a bond, we make a bond, we break a bond. So now we're withdrawing electron density out of the benzene ring to this electronegative oxygen atom. So we form a resonance structure with the double-headed arrows of now benzene being now electron poor, with electron density now localized on your exocyclic oxygen atom, and a carbocation now on this carbon nucleus. So now the positive charge and decreased electron density or electron cloud around the carbon nucleus makes this carbon de-shielded. And when we de-shielded, we go down field shifted, going at a higher ppm value. That's why we have higher ppm value than that 128.